All right, so I think it's time we can start today. So welcome everybody to the second day of the Quasars and Galaxies Through Cosmic Time conference. Yesterday we had a great lineup of talks, and today I'm also very excited about the talks as well as the discussion session. Yesterday's was also great, the discussion session. So actually we don't have any announcements to make. So we'll just move on directly to the talks. So I'll leave you now with the host of the first session, Manuel Aravena. So go ahead, Manuel.
Yeah, thank you, Roberto. So as Roberto said, I'm Manuel Aravena. I'm a faculty at UDP, and I'll be the moderator this morning. So in our first talk of this morning, the invited talk, we have Feige Wang from the University of Arizona, and he'll be talking about proving the most distant quasars under environments. So I'll leave you with Feige. Please go ahead.
Thanks. Can you see my slide?
Yes, perfect.
Okay, hello everyone. I first of all want to thank Judge and Roberto and all other associate members to organize this wonderful conference. So today I'll talk about how to prove the most distant quasars and their environment with the current and upcoming facilities. So many of the work in this talk is co-led by Jin Yang and myself, and also by collaborating with a large team. So in this talk, I will talk three small pieces. The first one is the distant quasar surveys and the rapid evolution of the most distant quasars. And then I will move to on a bigger scale to talk about the host galaxies of these earliest supermassive black holes. Finally, I will talk about even larger scale, the basically larger scale environment of the most distant quasars. So let's start with some introductions. After 400,000 years of the Big Bang, the universe cooled enough for the primordial plasma cooled down to form the first hydrogen atoms and start the dark age. With the universe continues to cool down, the overdensity of the primordial primordial hydrogens cooled down to form the first generation stars, galaxies, and quasars and black holes. So the quasars as the most luminous non-transient object provide as a lighthouse to study those crucial epoch. We call it the epoch of renaissance. So for this talk, I will mostly focus on quasars in this epoch. So for the quasars, what else we can understand by studying those quasars? First of all, the quasar is powered by the accreting supermassive black hole. So by studying quasars, is basically by studying the earliest generation accreting supermassive black holes, and the growth of the first generation supermassive black hole is basically limited by the available accreting time. So if you can find billion solar mass black holes at redshift 6, which means the black hole has to be growing at any limit since the first generation starts formed. And if you can find even more distant quasar, which means you can put even stronger constraints on the seed black hole and its growth track. So to a larger scale, the quasar that is hosted by massive galaxies. In our local universe, we have known that there is a tight relation between the mass of the supermassive black holes and the mass of their host galaxies, and which suggests that the black holes and their host galaxies co-evolve with each other. But at high-redshift universe, we still have very little information about whether the black holes and their host galaxies co-evolve with each other. Although there are many observations of the quasar host galaxies using ALMA and MUSE, we still cannot give a certain answer whether the black hole and their host galaxy co-evolves, or the black hole grew first, or the galaxy grew first. So this is one of the big questions we wanted to answer in the past decade and also in the future with GWST. So to a larger scale, so those luminous quasars are the most rare object in our universe and has been thought to be traced by the most best halos. And in this slide, I show two roomy volume of a cosmological simulation. In the left, which basically shows a volume with a density of similar with the critical density of our universe. And in the right panel shows a very overdense region. So those black dots are indicates the location of black holes, and the small dots indicates 10 to 6 solar mass black holes, while the big dots indicate the location of 10 to 9 solar mass black holes. So in these two figures, you can see that the billion mass supermassive black holes can only be found in the most overdensity regions and traced by the most massive halos at redshift 6. So this simulation suggests that the supermassive black hole can grow to 10 to 9 solar masses by redshift 6 only in the most massive halos without invoking any super-annular accretion, and those massive halos are situated in the most overdense regions. So by studying those earliest billion solar mass black holes, it basically could allow us to study the earliest large-scale structure of the earliest overdensity of the universe. So that's why we wanted to study the quasars, find those distant quasars, and study the quasars in multi-scales and also multi-phase. So let's now we talk about the distant quasar surveys and the rapid evolution of these quasars. As I said, the quasars can provide many important information about the early universe, but they are extremely rare. And in the left panel, I show the density evolution of quasars. You can see that the density of quasars peaks at redshift about 2 to 3, but declines very fast towards higher redshift. At redshift 6, it's only about 1 quasar per 100 square degree of the sky for the billion mass solar mass black holes. And on the other hand, in the right panel, I show the density of quasars and other contaminants, basically objects in our universe with similar colors with quasars. You can see that the majority of the MLT dwarfs in our Milky Way and also early type galaxies in our universe has a much larger number density than quasars, which makes it difficult. It's extremely difficult to find those quasars. I will not talk about the details on finding those quasars, but I will briefly summarize what people have done in the last decade. So in the left panel here, I show the quasar luminal function measured from the Sloan and CFST quasar surveys showing in these black dots. So people still keep improving the statistics of the quasar luminal function in the bright end at redshift 6, but in the last couple of years, the people have one big improvement is in the faint end by the Subaru quasar survey, we call it CELX. So I believe Michael have talked about this yesterday, but here you can see the latest luminal function measurement from the by combining all the faint quasars and the bright quasars we have known in the past. We have known now. So the other focus is to push finding the most distant quasars of finding the earliest billion solar mass black holes, which is my focus in the past few years. But in order to find those very distant quasars, you really need a wide area sky survey. In addition, the lemma alpha, the mean feature of the quasars in the spectra is restricted to infrared if you go to redshift beyond 7. So you really need both optical and infrared imaging in order to find those distant quasars. Fortunately, in the past several years, there are many major sky surveys have made it possible. Like especially we have the DAISY legacy imaging surveys in the optical, in the northern hemisphere survey, and also there is a dark energy survey we all know in the south. In the infrared, we have the Euclid hemisphere survey and the UKIS survey in the north and the west hemisphere survey in the south. So the combination of those imaging surveys provide us about 20,000 square degree of the sky covered both optical and infrared surveys, allowing us to build up the first sample of luminous quasar I received around 7. Again, I will not talk about the details on how to find those quasars, but I will show you the results has been made, the progress has been made in the past several years. So in the left panel, the plot shows the spectra of some examples of those luminous quasars. You can see that from the highest redshift at redshift 7.6. In summary about this, there to date, there are about 6 quasars have been found at redshift beyond 6.5, and there are 8 quasars at redshift beyond 7, including 3 quasars at redshift beyond 7.5. So in this plot, I show the distribution of the luminosity and redshift of all those known luminous quasars. So those red points are basically the new quasars discovered in the past several years by our team, and the blue points are quasars discovered by others, mostly in the faint end by the Subaru team. So as I said, there are 3 quasars at redshift beyond 7.5. This marks the current quasar redshift frontier. The first 7.5 quasar was discovered by Eduardo. And in the past few years, I highlighted these 2 new quasars. One is at 7.52 and the other at 7.6. You can see the spectra, the beautiful spectra of them. So all these 3 luminous quasars hosting about 1 billion solar mass black holes, and also the other few quasars at redshift beyond 7 also host very massive black holes. So in the right panel, I show the black hole growth track of those redshift 7 quasars or the redshift 7 supermassive black holes. You can see that. So in order to grow those first billion solar mass black holes, you really needed to grow from very early epoch and grew from a very seed massive black hole. If you assume the seed black hole has been growing at an limit. So the discovery of this quasar really put strong constraints on the seed black hole masses and their formation mechanisms. So these are the most distant ones. So by combining all the quasars we have known up to from redshift 6.5 to 7 to redshift 7 is we can measure the density of those luminous quasars finally. And again, let's back to the density evolution plot of quasars. So these orange data points shows the recent measurement of the redshift 7 quasar. You can see that from redshift 3 to redshift 6, the quasar density is basically declining as exponentially, but at redshift beyond 7, the decline rate is even higher, which means that the quasar evolution is very fast. The quasar density decreased by a factor of 2.6 within just 120 million years. So this is a really short time. Remember that the e-folding time of black hole growth is about 50 million years. So it's only about 2 e-folding time for the black hole growth, but the density decreased by 2.6, which is a big factor within such a short time. So the density of this quasar evolves rapidly. Then we want to understand why it has such rapid evolution, whether the black holes or quasars has different properties at those earliest epochs. So first of all, I would show you the black hole mass and the adenine ratio of these black holes. So in the left plot, I show the black hole mass versus the volumetric luminosity of those earliest supermassive black holes as shown in the red squares, while the gray dots are basically low redshift quasars in the Sloan quasar survey, as well as I highlight some redshift 6 quasars discovered in the past years. And you can see that those luminous redshift 7 quasars also have like a billion solar mass black holes and similar with redshift 6 quasars, but they have occupied different regions in this plot, which are close to this dashed line. We call it adenine limit operation, as we saw in the right panel, basically the distribution of the adenine ratio. So you can see that the red line shows the redshift 6.5 quasars, while the blue line shows the luminosity mass, the low redshift quasars in the Sloan digital sky survey. You can see that those luminous quasars are really occurring at adenine limit. This result is not surprising. It's similar with redshift 6 quasars, but let's look further to see whether they have other different features in the spectra. The left plot, I show the blue shift of carbon-4 emission line. So the carbon-4 emission line is the high ionization emission line, where the magnesium 2 line is the low ionization emission line, which is a better tracer of the quasar intrinsic redshift. So the blue shift of these 2 lines, it basically indicates there are some strong outflows in the quasar system. So in this plot, I show the blue shift of the carbon-4 emission line as a function of redshift, you can see that most of this luminous quasar shows outflows with the carbon-4 blue shift bigger than 1,000 kilometers per second. And also you can see that there is a trend of stronger blue shift of carbon-4 lines towards higher redshift, which is very interesting, suggesting those highest redshift quasars, so the stronger outflows. So the outflows cannot only be seen in the emission line, but also in the absorption line, because when the driving outflow launched from the accretion disk can absorb the flux emitted from the accretion disk, and we can see those outflows as the broader absorption line feature in the quasar spectra. So in the right panel, I show two examples. One shows the redshift 7 quasars, which you can see there's several absorption troughs. I highlight the carbon-4 absorption trough at a those absorption troughs are blue shifted a lot, which means the outflow is at a very high velocity. And also in the bottom panel, so the outflow we see is the most distant quasars. So all these quasar outflows have a velocity of close to 10% of the speed of light, which is pretty high. And in addition to the detection of those really extremely high velocity outflows, we also see that there are a large fraction of quasars at this redshift. So such features, they are about 30% of them. So the strong outflows, although not at such high velocity, but the fraction is about 30%, which is about twice as high as that found in the low redshift. So which again suggests that those earliest supermassive black holes are having the very strong outflows. So these strong outflows could have affected the star formation in their host galaxies, but to our limited to the sensitivity of existing facilities, we cannot know the details about how the outflows affect their host galaxies. But with the GWST, we would be able to see such feature. So before I move further, I wanted to highlight one thing is, as I said, to finding those luminous quasars really requires a very wide area imaging survey. But we already used like about half of the sky to the current limit. But in the next decade, there will be 3 main methods that will push our understanding to even earlier epoch and to fainter end. Basically, the LSST or the Rubin Observatory provide a very deep optical imaging survey, and the Romain and the Euclid will provide infrared imaging survey. So the combination of these surveys will finally enable us to find the first redshift 8 quasars or even redshift 9 quasars, and to build up a much larger sample of quasars at redshift beyond 6 and 7. But this is to finding those quasars. All these surveys are mostly imaging surveys. So in order to identify these quasars, we need a spectroscopic follow-up, and we need ELTs for this. So this is about the quasar survey and the rapid evolution of those distant quasars. Next, I wanted to move to a bigger scale to talk about the host galaxies of these earliest supermassive black holes. So as I said, those luminous quasars are very bright, and the light is dominated by the emission from the accretion disk, which makes it's extremely difficult to detect the host galaxies in the redshift frame UV. So in the past decade, people have played many efforts trying to detect the host galaxies with HSD, but to date there is no any stellar light is detected from those distant quasar host galaxies. So there will be a talk on Thursday focusing on this, but I will not talk about it in detail here. But if we look at the SED, the spectral energy distribution of quasars, as shown here, in the redshift frame UV, the light is dominated by the accretion disk. But in the far infrared, it's different. So there are strong emissions from the dust in the quasar host galaxies, which means we can detect the host galaxy in the far infrared, redshift frame far infrared. In addition to the dust continuum, there are also many other important emission lines, like the C+ emission line, which is a principal ISM coolant, and the brightest far infrared line. and also good star formation tracer. And also there are many CO lines which are great tracer for the cold gas. So by detecting those far infrared dust emission and emission lines, we can also gain insight into the quasar host galaxies. So in the past years, several years, so extensive observations have been performed, try to detecting those quasar host galaxies and try to know the kinematics of the galaxies and to measure the dynamical mass of these quasar host galaxies. Here I show some examples from the ALMA observations of redshift 6 quasars, and this is some examples showing the C+ emission of the quasar host galaxy, and also the velocity map of the C+ emissions. So in the right panel, basically another large sample of redshift 6 quasar host galaxies in the C+. This image, this survey are led by the MPIA team. So from this detection, from the detection of the C+ emission line from the quasar host galaxies, we can gain insights into the dynamical mass of the quasar host galaxies. Let's back to the relation between the supermassive black hole and their host galaxies as shown in the left plot, also the similar plot of the M sigma relation in the right plot. So all these plots show that the supermassive black hole in this plot like sails higher at a higher placing than the expected values from the local relation, which indicates that the supermassive black hole is overmassive at an early epoch, and indicates that the black hole could grow earlier than their host galaxies. But again, there are still lots of uncertainties in both parameters here. The host galaxies are the dynamical mass of host galaxies are from the gas kinematics, but in many cases it's from the emission line Ys, which are still uncertain because we only marginally resolved the quasar host galaxy, or even didn't resolve the quasar host galaxy. So we still need to go to very high resolution and to resolve the quasar host galaxy to get a better understanding, better measurement of the dynamical mass. So this observation have been focused on redshift 6, although there are several quasars at redshift beyond 6.5 has been detected with ALMA. But as I said, in the past several years, we have made a much larger sample of quasars at redshift beyond 6.5. So we really also wanted to detect the host galaxies of these quasar host galaxies of these quasars. So in order to do this, we performed a new ALMA survey trying to detect the host galaxies of quasars at redshift beyond 6.5. In the plot, again, I show the distribution of the luminosity and the redshift of the earliest quasars. You can see that. So these orange data points are basically the quasars we are targeting with ALMA, and the blue points are the known quasars at with ALMA detections, and the black points are objects still lack ALMA observations. So our survey is trying to build up the ALMA detection of a large sample of quasars at redshift beyond 6.5, and all of them are bright, like with the magnitude brighter than -25, which means they are hosting billion solar mass black holes if you assume the adenine limit accuracy. So let's show you the basic results here. In the left, I show again the C+ emission of those quasar host galaxies, and in the right panel, I show the spectra of the C+ emission. So among the 30 quasar host galaxies we have been observed, 100% of them are detected in the dust continuum, and more than 90% of them are detected in the C+ emission lines, which suggests that all those redshift 7 quasar host galaxies are have a large amount of dust and gas in the host galaxies, indicating extensive star formation activity in the quasar host galaxies. So in addition to detect the host galaxies, we can also try to understand their kinematics. In this plot, I show the left column, I show the integrated C+ flux, C+ emission of the quasar host galaxies, and in the middle part, I show the velocity map of the quasar host galaxy, and in the right column, I show this dispersing map of the quasar host galaxies. So from this plot, you can see that they have very different kinematics. Like the top two shows a clear velocity gradient, indicating this system are supported by rotation by rotating disk, while the other two shows does not has such features. This one is just compact, and this one is more like a tidal disrupt featured. So from these observations, we have known that those quasar host galaxies are very compact with a size half-light radius size about 2.3 kiloparsec, and the C+ is more extended than the dust emission. And in addition, like 50% of them showing rotation supported kinematics, but the other half of them showing random motions or merge-like. But there one common feature of all these galaxies. All the galaxies are very turbulent with a very high turbulent gas, and yeah. So from this kinematics, we can measure the dynamical mass of these quasar host galaxies. Again, similar with the redshift 6 quasar host galaxy studies, and we put it again on this plot, the black hole mass versus the dynamical mass of the quasar host galaxies. So those orange points are showing this redshift 7 quasar host galaxies. Again, they are similar with the redshift 6 quasar host galaxies, which lie above the local releasing and suggesting they have overmassive black holes. But again, in this plot, all the quantities still have large uncertainties, which need to be improved with future observations. Either very high resolution observations from ALMA allow us detailed kinematics modeling, or with the GWST observations to detect the stellar light and also improve the black hole mass measurement. So we are following up this with both ALMA and GWST of these quasar samples. In the last part of my talk, I will briefly go over the large scale environment of the most distant quasars. As I said, we have those rare distant quasars has been thought residing in the most massive halos and traced by galaxy overdensities. So in the past 10 years, people have made a great effort trying to detect such overdensities around quasars, but there are still very little evidence seeing that they are located in the overdensities. Here I show some examples. All these quasars are highlighted by red colors, showing they are located in overdensity of lemma break galaxies, but the blue colors shows quasars does not have overdensity of star-forming galaxies in their vicinity, which is a bit confusing. These observations are from HST imaging by selecting the lemma break galaxies. But HST has a very small field of view. If we go to ground, we can from ground we can target a larger area or larger field of view, but with a shallow depth. Again, it has similar results. Like some quasars does not reside in the overdensity of lemma break galaxies, but some of them shows overdensity of galaxies, which has very confusing. But anyway, there are some cases have been confirmed to be of a quasar to be residing in the overdensity of star-forming galaxies. Here I show an example of a redshift 6.3 quasar, and you can see in both small scales and large scales, it has a lot of lemma alpha emitter or lemma break galaxies at a similar redshift with a quasar, suggesting the quasar residing in the large scale overdensity of star-forming galaxies. But this is only one of few cases have been confirmed. In order to confirm such overdensity, it's extremely difficult with broadband imaging plus spectroscopy follow-up. So what I summarize the difficulty here. The HST field of view is too small, and both HST and ground observations are mostly targeted for targeting the lemma break galaxies with only few filters. So the redshift uncertainty of the selected lemma break galaxies are huge, and the signal of the overdensity is basically washed out by the projection effect. And also all these observations are only sensitive to the unobscured galaxies, and currently there are only a small sample have been targeted, so affected by the cosmic environments. So in order to against all these difficulties, we are trying to other methods trying to detect those overdensities using the narrowband imaging. And also we need a multi-wavelength follow-ups. So also in the following talks I listed here, we will also talk about to start the efforts to study the environment of these quasars. But here I will show you one effort I'm leading now is trying to use a narrowband filter on the Magellan MX and also Subaru HSC. We selected a sample of redshift 6.6 quasars and trying to use narrowband to select the lemma alpha emitters around the quasars. Well, the lemma alpha emitter, the benefit of lemma alpha emitters is they have a very small redshift uncertainties compared to the lemma break galaxies. So you can directly pick up the galaxies physically associated to the central quasar. We also targeting. Okay, sorry. Yeah, we also targeting the 6 quasar addresses 6.7 with SST. So these observations will basically covering a large volume and provide a small uncertainties, redshift uncertainty of the selected galaxies. And we are trying to cover the large quasar sample against the cosmic variance. But due to the pandemic, the observations are significantly delayed. But here I show you a very preliminary result. In the left panel, I show the distribution of the lemma alpha emitters in a quasar field at redshift 6.6. You can see that this color map is basically the density, the surface density of the lemma alpha emitter. The red part shows the overdensity, while the blue dots here indicate the placing of quasars. You can see that the quasar is located in a overdensity of lemma alpha emitter. So not only in the lemma alpha emitter, we also follow up this field with ALMA, very high resolution and very very deep observations. From this plot, the zooming part of the ALMA observation, you can see that the quasar itself is a merger galaxy. It has a companion galaxy, and also in the nearby region, it has another 2 galaxies at a quasar redshift, as shown in this column. All this column shows the spectra, the C+ spectra of the both quasars and galaxies. Indicating these galaxies are at the similar redshift with the quasar. And in addition to the spectral follow-up of the C+ emitters, we also took some spectral follow-up for the lemma alpha emitters. And today we have already confirmed more than 10 galaxies at redshift 6.6 associated with the quasars. So this observation indicates the powerful narrowband selection and indicate the quasars located in the overdensity regions. So this is the early preliminary results. Yeah, I will have one slide. Out of time. Yeah, thanks for the reminder. So in order to, as I said here, the quasar located in overdensity regions, but it's not only in the unobscured phase, but also obscured phase. So in order to study this, we made a program with the GWST. So we have known that the GWST is already inserted to the L2 orbits yesterday, and we hope we can to start using GWST to do our science in the coming years. And here I should highlight one program led by myself and my collaborators. It's a medium-sized program. We are trying to target 25 quasars with a near-time slitless imaging, and to basically to target all the galaxies in the quasar field, and to find out whether these quasars are located in the overdense regions. And I will skip this slide. Basically, we are trying to follow up with these quasar fields with many different follow-up observations. And finally, I leave my talk here, basically summarize all the approved GWST programs, both GTO and GEO programs, trying to target those distant quasars. I hope we will know more about those very distant quasars with the GWST observations. I will stop here and happy to.
Thank you, Finch. There are a lot of questions, so probably we have time for a couple of questions only. So I'll start with one that received most votes from Girish Kulkarni. So here she is asking, has it been possible to estimate the lifetimes for redshift 7.5 quasars from their proximity zones?
Yeah, that's a good question. The answer is yes. We actually, so for redshift 7.5 quasars, there are 3 of them, right? So 2 of them does not have the broad absorption line quasar, making it possible to using the proximity room effect to like constrain both the quasar lifetime and the damping wing profile and to measure the neutral fraction. And all these 27.5 quasars have been measured the lifetime using the proximity room.
Great. Thank you very much. So Michael Strauss is asking a very interesting talk, Feige, on the plot of the C4 outflows as a function of redshift. Are there any redshift-dependent selection effects in the sample used? For example, does the sample have the same luminosity distribution at all redshifts shown?
Yeah, that's a great question. So all these data points shown in this plot are basically luminosity matched to the redshift 7 quasars. So they are luminosity matched sample. Regarding the selection, so all these quasars, especially redshift beyond 6, they are selected using the standard dropout candidates. There is no obvious bias between redshift 6 and redshift 7 samples. Yeah.
Right. Thank you. So now James Ayert is asking, at lower redshifts, we think AGN are found in dense environments, but probably not more than expected given their host, massive galaxies. Could this also be the case at very high redshifts, and could this explain some of the discrepancies between some results finding over versus under dense?
Yeah, that's a great question. So it's possible, but it's very unlikely. The reason is because those very high redshift quasars like hosting very massive supermassive black holes, indicating their lifetime, I mean, their duty cycle is high, close to unity. Otherwise, you cannot grow such massive black holes. So the duty cycle of these quasars is higher than the low redshift quasars, which means they are indeed rare, the most biased object in the early universe and tracing the most biased halos. So I mean, I cannot give the definite answer now, but the GWST will answer this question, especially the program I just highlighted, which is the main goal of our program. So we will measure the dark matter halo mass and measure the quasar galactic cross-correlating function of this quasar sample, and trying to answer whether like all the quasars are in massive halos, or all the quasar dark matter halo has a broad range. So we will know this with the James Webb.
Thank you very much. Manda Banerjee is asking, thanks for a great talk. Could you comment on how you estimate the incompleteness selection function for your high redshift selection method to calculate the quasar space density at redshift 7? Okay,
great. So great question. So in order to estimate the selection or the completeness of our selection, so we performed the simulated quasar sample at redshift 7, covering all the luminosity and with different like line strengths, like using, of course, we're using the Sloan low redshift quasar as an example to basically give you the space, all the give you all the properties of the emission lines, and we simulated a large sample of quasar at redshift 7 with similar line strengths and power law distributions of the similar with the low redshift quasar, and using that simulated quasars, we apply all the criteria we applied to the photometric data and to calculate the selective function and correct the incompleteness. We can talk about this in detail, yeah, in the slide.
Great. One last question from Melanie Habuzid. Great talk. Could the underdense fields of high redshift quasars be due to powerful feedback from the quasars over cosmic time, preventing galaxy formation in the quasar surroundings? Is it consistent with the large outflows that you see?
That's a great question. So I would say those underdensities are probably not real underdensities, again, because limited by the current observations like the cellular depths and the uncertainty of the redshift of the galaxies. So I wanted to say we are still not sure whether they are underdensities. And in terms of whether the quasar outflow can affect the environment, we still don't know. hopefully we can have more insights with the GWST, like if we can confirm those some quasars locate in the underdensities and they are related to the outflows, that would be really cool, which means the quasar outflow could affect the very large scale environment. But but currently I don't think we know the answer yet.
Excellent. Well, thank you, Feige, for this great talk.
Thank you.
It's raised a lot of interest among the audience. There are a lot of other questions that are going to be in Slack. So please go and check there to answer the rest of the questions.
Yeah, sure.
And when we now move to the next talk by John Weaver from the Cosmic Dawn Center in Copenhagen about Cosmos 2020. So please, John.
Great. Good morning, everyone. Good afternoon, wherever you are. Thank you to the organizers of this meeting for giving me the opportunity to talk with you all today. I want to thank my collaborators listed here. And now I'm going to spend a little bit of your time talking about Cosmos 2020 and our insights we've gained into galaxy formation and growth in the first 10 billion years. I also want to thank Feige for setting up this talk. That was a great review talk, and I hope to continue on this theme of massive galaxies. Not so much AGN, but the massive galaxies anyway. So while massive galaxies are common in the local universe, we know that they are extraordinarily rare in the distant early universe. However, they do exist, as evidenced by this lens galaxy here. At about an age of 3 billion years after the Big Bang, it shows a remarkably old, mature stellar population, a population so old that we struggle to explain it with our common assumptions about the operation of galaxy evolution and physical processes within that time period, the first 3 billion years. And so currently, our theory and our assumptions struggle to explain the rapid formation and growth of these most massive systems found at early times. We know they must have been amongst the first galaxies to form. And as Feige was talking about, right, they must be seated in these overdense peaks, these overdense regions from the primordial web of dark matter, and must have been encased in the gas from which they grew, which then, of course, subsequent star formation, the building, the growth of their stellar mass, expelled UV radiation to their environment, kicking off the epoch of reionization. Now, the questions that I'm interested in asking about these massive galaxies are how did they form and evolve? And what are the physical processes which were responsible for their extreme growth? To do so, we constructed Cosmos 2020. It's a near-infrared selected catalog of about 1 million galaxies over the 2 square degrees of the cosmos field, unique for its large area and near-infrared depth. On the right-hand side here, I give you just a very zoomed-in region of the survey, just to give you an appreciation of the crowding we see from these very deep near-infrared ground-based images. To photometer all of these galaxies, we use 2 photometry techniques. The first one we're going to call classic. This is basically the same as in Cosmos 2015, if any of you are familiar with that, where we primarily extract fluxes as measured in apertures. Now, we also pair it with the Farmer, which is a more recent photometry software built on the tractor by Dustin Wang and David Hogg, which fits fluxes via models, profile fitting. And so for these 2 sources on the right-hand side that are very close to each other, even 2 arcsecond diameter apertures cannot hope to separate their flux. However, on the right-hand side, I showed that models from the Farmer are able to do this automatically. More so when you're moving into to a lower resolution regime, such as the infrared from Spitzer IRAC, this becomes incredibly important and an advantage. Now we pair both of these photometry catalogs with 2 photo Z codes, LaFar and EASY, such that every one of our 1 million galaxies has 4 measurements of photometric redshifts, mass, UV luminosity, etc. Now with this catalog, I'm interested in measuring galaxy growth as measured by the galaxy stellar mass function. The deep imaging of the 2 square degrees of cosmos means we have more complete mass selected samples of galaxies, and the wide area, just as Feige was talking about, enables us to catch those rare massive galaxies. On the left-hand side here, I show photometric redshift versus log stellar mass, noting our mass completeness limit estimate here in yellow. Now I'm going to take a vertical slice of this 2D parameter space to construct or measure the galaxy stellar mass function, shown on the right-hand side for redshift about 0.3. You can see that the low mass galaxies are very common, whereas high mass galaxies are comparably rare. And there's a knee in that stellar mass function beyond which is the realm of the most massive galaxies. Now I'm going to rewind the clock and we're going to watch the galaxy stellar mass function evolve backwards in time. It's going to lose that knee and become much flatter to resemble a fairly straight stellar mass function by about redshift 4. Comparing with state-of-the-art hydrodynamical and semi-analytical models, just two chosen here, Shark and Eagle, relative to them, we find an excess of massive galaxies within the first 1.5 billion years. Now, if they're genuine, and of course, AGN can be affecting us here, and I don't have enough time to speculate on that more just now. Feel free to ask me those questions later on or talk to me on Slack. Such remarkably mature galaxies, if they are genuine, would strongly challenge our theoretical models and assumptions of galaxy evolution on the massive end at these redshifts. Now, I also want to quickly mention, if we take the redshift versus stellar mass plane and take, instead of vertical slices, rather we take horizontal slices and look at the number density of sources in bins of mass, you can see how the buildup of stellar mass is enormously constant, remarkably constant, across all mass regimes from about redshift 5 all the way up to redshift 1, after which we see the downturning of the number density of the most massive systems, which is consistent with observations, of course, and well-known observations in the low redshift universe. Now, currently, we cannot directly measure galaxy stellar masses above redshift 7. However, we can measure their UV emission above redshift 7 to learn about their star formation, in other words, their growth. So this is, of course, the UV luminosity function. We provide new constraints in the first ultraluminous galaxies in Kaufman, Weaver et al. Submitted. We find 31 galaxy candidates above redshift 7.5 over the 1.4 square degree area of secure area of the 2 square degree Cosmos survey. Importantly, we find new sources only found with our model-based photometry in the Farmer, which were not selected in the apertures due to crowding in the bluer bands, which does not permit a high redshift solution. Now, in terms of the science, we know at low redshifts, the UVLF turns over in response to feedback mechanisms or other mechanisms, as is discussed in the literature, just an example shown here. However, we show that we contribute to the mounting evidence that at redshift 9 or so, the UVLF does not seem to be turning over. In fact, it seems like we are transitioning from a Schechter function fitted to lower luminosities to more of a broken power law, as discussed by several recent works in the literature. Now, this has several implications for galaxy evolution processing. Could quenching have not begun yet? Does dust complicate this picture? Or perhaps the role of AGN is becoming more noticeable? And all of these processes, as it stands, are difficult to discern based on our primarily photometric imaging.
Oh, 1 minute.
Thank you. I'm wrapping up. As it seems, we may be witnessing a pre-feedback stage of seemingly unrestricted growth, of almost unlimited star formation rate, where this galaxy can grow and grow and grow and grow unrestricted by the normal processes that govern galaxy evolution. However, currently no spectroscopic sample exists. To that note, I'm enormously happy to be the PI of a 14.4-hour JWST Cycle 1 program coming up called Beasts in the Bubbles, which will dissect 5 of these redshift 9 galaxies with IFU spectroscopy via NIRSpec. We will confirm the ultraluminous end of the UVLF at redshift 9, and also unveil all of the wonderful physical mechanisms governing the formation and evolution of these extremely early systems. The last thing I'll say before wrapping up is that the catalogs for Cosmos 2020 are now publicly available at this website here. Please go have a look. Details can be found in Weaver et al. 2022a. Thank you very much.
Thank you very much, John, for this very nice talk. So we have a couple of questions. The first one is by James Earl. So it's asking, could the excess of massive galaxies be an Eddington bias effect, which uncertainties in stellar masses scattering galaxies high?
Yes, absolutely. So thank you, James, for that question. I didn't have a time at this part to go into the Eddington bias. If we assume any reasonable measurement of an Eddington bias correction, that is a kernel, something like constructed in Hilbert or Davidson et al., where you take a Gaussian and a Lorentzian and combine them, we find that no reasonable assumptions there can allow us to get to that Schechter function as shown here. Instead, what might be the case is we may be noticing something more like a broken power law. However, I do caution that this sample, if you look at their SEDs more closely, resemble strict power laws. In other words, they very well may be AGN interlopers, which based on broadband photometry are enormously difficult to constrain the redshift and mass. So we have several programs going on right now from Keck, VLT, et cetera, to go and follow up these sources and try to discern what they are and if they should correctly be at this spot in the galaxy stellar mass function. Thanks.
So there are some other questions in the chat, but we'll post them in Slack because of a matter of time. So thank you, John, again for this very nice talk, and we'll continue with the next speaker, Romain Meyer. If you can share your slides.
Yes, of course. All right, can you see my slides?
No, I can't see them.
Oh, wait, sorry.
You might have shared a different window.
Yes, okay. Now you should see them.
Yes, that's perfect. Thank you.
Okay, thank you very much. All right, thank you very much. Thank you, everyone. Oh, sorry, you can't see me. Yes, all right. Thank you for the opportunity to speak here. I want to come back to high-redshift quasars and quasar overdensities. Feige has, of course, given a great talk, great summary talk, but I want to zoom in on one very specific problem that was discussed earlier, which is this issue of the growth of the supermassive black holes. And so I think one of the most puzzling results, right, of the discovery of redshift 7 quasars, even some at redshift 6.3, is that they're so massive that you need to have them grow all of their life, basically, at Eddington rates, and or start from supermassive, 10 to the 4, 10 to the 5 seeds. And so extreme seeds or extreme accretion for their entire lifetime is possible. But as theorists tell us, this is only possible in their models if these quasars are also located in the most overdense regions in the universe. And so quasars, being these rare enormous sources, probe the very first overdensities in the universe, which is great because this has a clear prediction, which is that around this quasar, we should find a lot of galaxies. Now, the difference between the prediction and the observation is, in that case, very wide, and there has been many attempts to do that, and the results are very contrasted. But we'll still continue to do that because if we confirm and if we can quantify these overdensities, we can hopefully put very interesting constraints on the formation of massive black holes and then their growth through cosmic time in the first billion years. So this is exactly what we've been doing in this study, taking a bit different approach than earlier studies that use LAEs and BGs. What we focused on here is 3 high redshift quasars, so redshift 6.5, looked at by a large survey with SCUBA-2 data. So with SCUBA-2, you're looking at a very large scale. So what you can see here are 3 maps with SCUBA-2 of these quasars that are in the center in red. And you can see that we have these 4 sigma detections that are circled in blue, and you have 4 to even like 10 in one of the fields. And this is, compared to the depth of this survey, this is a lot of SMGs. And these quasars were well known already because in the team at MPIA, we published a series of papers where they were found to have C2 companions. So that's on the very small scales, so that's on kiloparsec scales. So you have these companions on small scales, and suddenly you have these potentially SMGs on large scales at 1, 2, 3, 5 megaparsecs. And so the question is, do these SMGs live at the redshift of the quasars? Because if they do, then this is bingo. This is the overdensity we've been talking about. So we went to these SMGs with ALMA, and we found that 12 out of 17 we detect them in a continuum, which is quite good. If you look at other studies of SMGs, lower redshift, when they look at them with ALMA, it's about the same ratio that you find. Some of them have like two objects. They break up in the ALMA because the difference between the SCUBA and the ALMA beam is very, it's quite big. But this does not answer a question, which is, are they at the redshift of the quasar? So we looked at the lines with ALMA. Of course, it's a data cube. You can look for a C+ line that would indicate that it's a redshift of the quasar. And in one of the fields, so that's the PJ231 in orange here, we'll have nice detections. What we found instead of the C+ line and redshift 6 was CO and C1 line and redshift 2.4. all of them are at redshift 2.4, and it's a complete luck that we have these lines in the same spectral tuning, because the tuning is very small compared to with ALMA. It's not a spectrograph, it's really ALMA, so it's 4 gigahertz. We're really sure this is the case, that they are at 2.4, because although the lines, some of them are a bit low signal to noise, if you look at the near-infrared spectrum of this object, there is a very nice magnesium 2 absorber here that is centered at velocity of 0. And the orange lines show you the velocity offsets of all the SMGs. And so it's quite nice, but this is not really my kind of science. This is a low redshift protocluster CGM enhancement. So let's go back and try to find if the other SMGs are at high redshift. So in all the others SMG, what we found is only 2 very weak lines. You can see here the emission maps, and this is 3.1, 4.3 sigma. I wouldn't call these detections with ALMA. And we also ran a search for C+ line emitter. I won't have the time to talk about this, but basically there were no lines that indicated that these SMGs were at the redshift of quasars. The problem with no line is you don't know if it's like you don't detect C+, and therefore it's an interesting galaxy and it's high redshift, or if it's just low redshift and you had no luck. So we went back to the archive where we had ancillary data. So we used HST and Spitzer imaging with the ALMA and SCUBA to construct RAF SED from the Resprim UV to the far infrared that we fitted with MagFizz. And basically the result is this one. For all of the SMGs, we get photos that are consistent with the solution at redshift 1, 2, 2, 3. And in the case, and this is again very consistent with CO and the C1 lines that we found in one of these fields. So these SMGs, I'm very sorry to report, are not at the redshift of the quasar. But we not only had ALMA, we also had MUSE. And so with MUSE, you can search on, again, the very small scales, the kiloparsec scales, for Lyman alpha emission. Yeah. And therefore, this is what we found. So we found 2 LAs around PJ231-20. So they are within 500 kilometers per second. So they're very close in redshift. So you can see in blue, here is the Lyman alpha emission, and in orange is where the Lyman alpha emission of the quasar is. And you can see the narrowband Lyman alpha emission. To this, you need to add that then one of the quasars was already searched for by Farina et al. In 2017, and they found 1 LAE. So basically, we're 3 LAEs around 3 quasars. So you might think, oh, 1 per field is not a lot, but actually at the luminosities that we probed, finding 1 LAE in this very thin slice in redshift space around the quasar, it's 1,000 times higher than the blank field density. So I want to finish this talk by doing a quick recap of what we know now about excess galaxies or high redshift quasars. So this is a pretty complicated plot, so we'll take it one step at a time. I'm showing the galaxy excess number density around high redshift quasars as a function of distance. So I'm just going to take a population of galaxy, compute the number density, and divide by the blank field number density. So the blank field number density here is at 1, either for LAs or C+. And you have these dotted lines that show the expectation from the quasar correlation measurements that you can, models that you can make and write down analytically. So here are the C+ companions revealed by ALMA pointings on these quasars. And you can see already the fact that we see companions in most or half of the quasars is very, very overdense compared to a random pointing in the blank field. And then we have our results here on the SMG. So again, we're constraining the very large scales here, 5 comoving megaparsecs, and here the LAEs combining Farina and our work. So what can you tell from this? Well, our constraints are very consistent with the C+ emitters. We just had to do this because if we detected something, it would mean these quasars live in crazy overdensity. They don't, they follow something that's more reasonable. And now we need to test this with more, let's say, intermediate scale ALMA mosaics. And you can also see there is a clear difference now. We have the statistics between the C+ emitters and the LAEs. And that might hint at the difference in evolution in environment around quasars between maybe dust-poor and dust-rich galaxies. So I don't have time to elaborate more on this. I will leave you with a conclusion. I just want to say this is very fresh. That was on the archive this morning. So have a look if you're interested by that paper. On Friday, I also put out another paper. So that's NOEMA observation of a redshift 6.4 quasar if you're more interested into kind of ISM view of high redshift quasars. Thank you.
Thank you very much, Romain. So while we're waiting for some questions in the chat, I have one. Actually, do you find in the MUSE of data some evidence for extended Lyman alpha emission in the fields?
So we haven't looked at the LAEs, but the quasars, of course, this has been already studied by Drake et al. And Farina et al. 2019 and 20. And yes, some of them have extended Lyman alpha nebulae around the quasars.
Okay. So one question from Cristobal Moya. It says, thank you for this talk, Romain. Do you think that it is a coincidence that the Lyman alpha lines you are finding are at higher redshift with respect to the quasar? Or perhaps one can only detect redshifted emission as the IgM absorbs flux around the rest frame wavelength?
Right. No, yeah, that's an interesting question. With two objects, it's hard to say, but it's clear that the quasar has a near zone that it's ionizing, and therefore it's affecting the transmission of Lyman alpha. If anything, you would think that it's easier to find Lyman alpha around high redshift quasars, and therefore maybe because it's at the back of the bubble, it's easier to transmit through the Lyman alpha bubble, through the ionized bubble created by the quasar. I don't think this is a significant bias though. Especially since I'm not really sure there are offsets between the Lyman alpha emission of the quasar, the C+ of the quasar. So the question of the systemic redshift here is a bit fuzzy. So I'm not sure 500 km per second is really, really significant there. But we'll see when we have more. I think the goal is to have more and more of these. Yeah.
Thank you very much. So further questions can be posted on Slack. So now we'll move to the next talk by Stefano Marchesi from Bologna. So if you want, you can share your slides.
Sure.
Thank you.
Do you see them? Okay.
Yes.
Perfect. Okay. Thanks a lot, everyone. Thanks for inviting me to give a talk here. It's a great pleasure. And so in this talk, I will present the results from this paper, which has been published just a couple of months ago. So the focus of this paper is the analysis of the J1030 field. You have heard a little bit more earlier on in the presentation. And as you have heard, this is the first field which has a redshift 6 greater than 6 over density that has been spectroscopically confirmed. This field has been targeted with also a deep Chandra observation in the X-rays, which makes it, as you can see here on the right, the 5th deepest field currently existing. The field contains a little bit more than 250 sources. The vast majority of them, thanks to the excellent coverage of the field, have an optical or near-infrared counterpart. And for 50% of the sample, we have a spectroscopic redshift. The remaining 120 sources have a photometric redshift. I leave the details of how the spectroscopic redshift and photometric redshift have been computed to the longer presentation that you can find in the online video. I just want to advertise our webpage where all this information is available, and you can also download the spectra and the SEDs. So if you want to play with our catalog, please go ahead. And so for this talk, instead, I will focus on two first scientific results that we got from this sample. Of course, this is just the start. We plan to do much more in the future, also complementing the X-ray data with radio data, and keep getting better and better imaging at different wavelengths. But the first results that we got based on this Chandra J1030 catalog can be summarized in two main topics. So the first one is the search for large-scale structures and the understanding and the confirmation that X-ray are an excellent tracker for large-scale structures. In this plot here, you see the cumulative distribution function on the y-axis as a function of redshift, starting from 0.1 and going up to 1.5 for both sources with a spectroscopic redshift that are X-ray detected, the black dots, and all the sources with a spectroscopic redshift in the J1030 field, the white dots. And as you can see, even a small number of sources detected in the X-rays, like is the case here, 4 sources with a redshift of about 0.15, are usually an excellent indication of a large-scale structure that can be confirmed at a much greater significance in the overall sample. So we were able to find a lot of structures in the Chandra sample, and the majority of them, as you can see, if not all of them, are confirmed with a larger significance once one takes into account the whole population. Just to give you an example, a visual example here, on the left, there's the Chandra field with all the different structures in different colors. On the right, there's a zoom in of the source at of the structure at the lowest redshift, 0.156. And here, the solid circles are those sources which have an X-ray counterpart. This is an optical image, of course. So a few sources have an X-ray counterpart, but many more at the same redshift are detected once we take into account also objects that are not X-ray detected. So this is a summary of the number of sources detected in each structure in the X-rays on the left and the overall sample on the right. And we know that this is efficient because the density of X-ray sources is very small compared to the optical. So even detecting just a few sources, even 3 objects in some cases, is a good indication of the existence of a much more extended structure. So this is a result that has been found in other deep fields, and it's confirmed indeed even in J1030. So the second result, the second scientific goal that we tackled is the search for high redshift objects, as it has already been discussed today and in general in this meeting. The search for high redshift sources is key to have a better understanding of the formation of the first structures in the universe. Indeed, this is also an important topic that can be tackled with deep X-ray observations. But there's an issue that we have, is that the fact that while nominally 25 sources in our sample, so more or less 10% of them, have a redshift greater than 3, only 3 have a spectroscopic redshift. Of course, sources that are at high redshift are on average fainter, and so it's more difficult to get a spec Z. So instead of using the nominal value of the photometric redshift, we decided to have a more statistically solid approach, and we use the probability distribution function that is associated to each source with a photometric redshift. So just to give you an example, this is a source for which we only have detection basically in the infrared. The nominal value of the photometric redshift is 5.7, but if we take a look at the probability distribution function, we see that really the source is the redshift that we can get is a lower limit of about 2. So while using this nominal value of 5.7 will be probably misleading, using the probability distribution function in a statistical way allow us to get a more accurate determination of the properties of the high redshift sample. So this said, we indeed find some interesting results, and what we see here are the number counts as redshift greater than 3 on the left and redshift greater than 4 on the right in the soft X-ray band for J1030 in red, compared with previous results from deep surveys like the one in the Chandra deep field from Vito et al. 2018, or the Chandra Cosmos Legacy, the orange squares, and from different predictions from X-ray luminosity function or AGN population synthesis models. And it seems that there's an evidence for an overdensity, particularly a redshift greater than 4. This can be seen a bit better in this next slide, where you can see that while at redshift in the redshift bin 3 to 4, there's a good agreement between the models and the data. Moving towards redshift 4.5 and 4 to 5 and 5 to 6, there's stronger evidence for an overdensity. The 2 different colors here mark 2 different photometric redshift codes that we tested, so that this is, we believe, a good validation of the fact that it's not, we are not biased by using a certain type of code. But nonetheless, as I mentioned earlier, the vast majority of the sources, actually all of them in bin redshift between 4 and 5, are only a photometric redshift. So we need to confirm these results with a spectroscopy campaign. If confirmed, it will be yes, it will be an excellent result because we already know that there are several overdensities here. So just to summarize a couple of future developments, one is in particular on these confirming high-redshift sources. We got time with LBT mods to target many candidates for redshift greater than 3 in our sample, which are shown here. And basically, we could get a redshift for 50% of them, a spectroscopic redshift. Notably, 2 sources, the one that you see on the right, with have a nominal redshift of greater than 5.3. So these will be the farthest X-ray selected AGN ever detected with a spectroscopic confirmation. The campaign will take place at the end of a month, so we'll see what happens. And the other thing is we are not directly involved, but this field is going to be targeted by James Webb with a GTO campaign. The field will be covered with both spectroscopy and photometry. And notably, about 20% of the Chandra sources will end up in the James Webb mask. So including 20% of the redshift greater than 3 candidates. So this field is of great interest for the community, and we are going also to benefit from the amazing data that James Webb will provide us in the nearby future. So I leave you with my conclusion. I hope I convinced you of the importance of this field to find obscured AGN, high redshift sources to track large-scale structures, and there's much more to come. So we look forward to new results and new exciting science on the J1030 field. Thanks a lot.
Thank you, Stefano. Very nice talk. So we're still waiting for some questions, but I have actually a question. So you're looking for overdensities based on X-ray sources, essentially in this field, but have you tried to cross-correlate that with a search for overdensities in other sources in other wavelengths, essentially from an optical near-infrared catalog, and see whether they coincide in position with the X-ray sources or so?
So that's a very good question. As you can see here, there's we think a good agreement, even spatially, in terms of the position of the structure. This is a zoom in of the majority of the sources are actually 0.16, the X-ray ones. And on the right here, you see that these are the 3 X-ray sources, and there are several of them not only at the same redshift, but also in a very, very close in terms of angular separation. So yes, it seems that the X-ray are a very good tracker. It's also possible, this is a field of view of about 8/8 arc minutes. So one would expect that these type of angular distances are still reasonable for a large-scale structure. At different redshifts. So the sources could be spread across the whole field of view of Chandra and still belong to the same structure.
Thank you. So we have one attendee that raised his hand. So we'll give it the chance to actually ask the question. He's saying, I know why your X-ray selection works well to identify large-scale structures. Sorry, I didn't say his name is Matt Malkan. So maybe, Matt, do you want to talk?
Yeah, okay, Stefano, if you can hear me,
yes.
I think this is extremely clever. And my hypothesis here is, as you probably know, the X-ray selection has already been shown to strongly favor picking up massive galaxies, which are infrared bright. I mean, exactly the kind of galaxies that you might expect would concentrate in large-scale structures, like clusters or early clusters. So you're using an effective tool which is sort of favoring finding the centers of these large structures. I could mention this. It's a paper which was published quite a few years ago, showing a remarkably strong correlation that the X-ray sources tend to be massive infrared bright galaxies, near infrared bright galaxies.
Okay, thanks. This is a very good suggestion. Yeah, we'll also explore. I think we can check also if that's the case even for our sample, since we have the photometry to measure if these objects, the properties of the host. So we're certainly going to do that.
Thank you very much, Matt and Stefano, for the questions. So the discussion can continue on Slack. We'll have to move on now. to the next talk by Kirsty Butler from Iran Grenoble. So she will be talking about molecular outflows at redshifts beyond 6. So please go ahead.
Alrighty, thanks for having me. My name's Kirsty Butler and I'm a brand new fellow at IRN Grenoble. But today I'm going to be talking about some work that I did for my thesis in Leiden with my supervisor Paul and some other co-authors listed here. So, molecular outflows from high redshift QSOs. Why do we care? So we know that outflows are an important part of galaxy evolution in general. They carry out metals, they carry out angular momentum and mass from our galaxies, which has an impact on the evolution of the host galaxy. And in particular for molecular outflows, we heard this yesterday, it's a phase that dominates the mass and the momentum budget of outflows. So this is a very important part of the outflow to target. And things that can eject gas from our galaxies is feedback associated with stars, but also from supermassive black holes, so active nuclei in the center of our galaxy. And we think that this is actually a very important mechanism in the most massive galaxies that we see in the universe. So that's the motivation behind the molecular phase, and we want to study these most massive galaxies. So here's the star formation rate density of the universe history. Just for reference, so we know that we have quiescent galaxies already down to redshift 4. And if you look at studies that look at this, then we expect that they have done most of their growth during redshift 6 to 7. So this is a part of the universe where we really want to study the impact. And for the most massive galaxies, which are the ones that live hard and die young and are quiescent early, we really want to study the impact of outflows ejected by the QSOs. So we target this redshift, but this is pretty far away. So looking at molecular outflows at this redshift, we have to be a bit smart about the techniques that we use. We can't use, well, we can try emission lines, but it's very hard. So instead, what we do, and this has been tried and tested and has been shown to be quite successful at detecting outflows at high redshift, is molecular absorption lines. So a very common absorption line that has been used both at low and high redshift is the 119 micron OH absorption line. So I'm showing you on the left some results from low redshift studies. It's a doublet and you can find it in absorption and emission. And one of the most important results from these studies at low redshift is that the outflow properties seem to correlate best with the AGN luminosity or the AGN fraction of these galaxies. So the more extreme the AGN, the more extreme your outflow. At high redshift, there's been not so many observations. There is a sample by Spilker et al. In 2020 that looked at a sample of dusty star-forming galaxies. And again, it was very successful at detecting outflows in these galaxies. I think it was about 73% of the sample. And a nice result that came out of this was that the outflows appeared to be clumpy. And these clumps were not necessarily cospatial with the continuum peak. There has also been a tentative detection of an outflow using OH in a high redshift QSO by Herrera Camus. But this is not so much information for QSOs at high redshift. We want to know more about the role that QSOs play in ejecting these outflows at high redshift. So that's where this project comes in. We asked ALMA if we could look at 3 far infrared bright QSO hosts at redshift greater than 6, and this is what we got. So I'm going to call them Quasar 1, 2, and 3. And what we found was the continuum at high signal to noise, but also a OH detection. So in the first QSO, and you can look at the bottom panels, perhaps that's easiest, we find the OH in absorption blue shifted by about 350 kilometers per second, so an outflow. In the second one, we find it in both absorption, blue shifted again by this time about 500 kilometers per second, and also emission at systemic velocity, so that's gas inside the galaxy. And then in the third, we didn't find an outflow or any absorption. It was just some tentative emission. So I will focus on these first 2 QSOs, the ones with the molecular outflows. So going forward, an aim of this project was not necessarily to get the most accurate result numbers for the outflows, but to compare these outflows with the other high redshift galaxies, so the dusty star forming galaxies that have been observed, and to see the difference between the outflows in these samples. So long story short, we measured the properties of these outflows, these absorption lines, and we used those properties to derive outflow properties. And we did this in the same way for the dusty star forming galaxies to compare the two. So the first one we go for is the mass outflow rate. Sorry, that should say mass outflow rate. And we just assume the same geometry. And what we show here in the field symbols is the upper limits, just to compare the two samples. So here we don't find anything strange. The QSOs are sort of in agreement with the dusty star forming galaxies, which we show in green. The QSOs are in orange. But things started to get interesting when we looked at the energetics of these outflows, which I will show here. So we have the kinetic energy flux and the momentum flux. And again, the dusty star forming galaxies in green follow a fairly tight relationship. And then we find our QSOs dropping down significantly. So naively, we were expecting to find more extreme molecular outflows like they saw in the low redshift studies. But here we're finding weaker outflows. So that was puzzling to us. So we thought, you know, what's going on here? What's the difference between these galaxies and their outflows? And one of the results from low redshift was that not only were these more extreme or heavier outflows from QSOs, but their velocity should be higher as well, so faster outflows. And that's not something that we found either. So this is the outflow velocity, and on the y-axis here is the infrared luminosity. So our QSOs were sort of lying at slower velocities. And one thing I thought we could try was assuming that your outflow comes out of your galaxy plane perpendicularly, perhaps we needed to make an inclination correction. So I took the inclination of the host galaxy, which was measured by kinematic data of the C2 line in another study. And I applied the inclination correction, and all of a sudden our QSOs started to agree with these dusty star forming galaxies. So I just ran with this. I redid the derivations for the mass outflow rate. This already sort of agreed with the dusty star forming galaxies. I show them now in the shaded orange. But again, it got interesting when we looked at the energetics. So our quasars initially were dropped down, way down below the dusty star forming galaxy, but with this inclination correction, all of a sudden they agreed very well with the dusty star forming galaxies. So just for now, assuming that this inclination correction does need to be made, what this implies to me is that these outflows are very similar to the ones that we see in the dusty star forming galaxies. And if you look at the sort of gray panels behind here as well, what that is showing you is that even at the upper limits that we derive here, star formation rate is also capable of driving these outflows. So there is no quasar needed. There is no quasar implied by what we see in the properties. So is the quasar even doing anything? And perhaps actually, maybe we should have thought maybe it wasn't. So there have been studies that have looked at the interaction between unobscured. So all three of these quasar are unobscured. So they've gone through their blowout phase and created a cavity in their ISM. And these have been studied before for their far infrared luminosity and their UV magnitude of the actual quasar. And what they have found is that there is no correlation between these two things. And what that implies is that there is not any interaction between the central quasar and the ISM around it. And this is from Feynman's 2018. This is for the global far infrared luminosity, but they went back and did it for the center in 2020. So even for the central part of the galaxy, they found no correlation. So, okay, maybe we should have looked at obscured
1 minute.
quasars. Thanks. Instead of unobscured quasars, perhaps we've just missed the phase where we've seen where the QSO is actually driving outflows. But there is one thing that remains now, and that is, why do we have to make this inclination correction for our QSOs, but not for the dusty star forming galaxies? Why do we have to do it? So it has been found before, and we find also for our QSOs that the host galaxy, and remember we're looking at absorption lines here. So what we see in our line is also dependent on the background continuum. And what has been found is that QSO hosts can be more compact than their dusty or their star forming friends. And if you assume this clumpy outflow and perhaps a fountain geometry, the impact that a more compact dust continuum can have on our observations, and also if your galaxy becomes more inclined, like our first quasar is, it can restrict your observations to clumps that are closer to the plane of your galaxy. So ones that have been perhaps ejected more recently, and perhaps are traveling at a more perpendicular direction from your plane before they sort of fall back down. And then you would need the inclination correction more than if you were sort of detecting clumps all over the place. Okay, so this is my conclusion slide. Maybe I can just leave it up, but I think in the future what we need is more galaxies, first of all, because this is only 2. We need spatially resolved observations so that we can really look at the geometry and test this. And I think it would also be interesting to look at these more obscured quasars to see if maybe we really have just missed the phase where the QSO is helping to drive molecular outflows, because I really think QSOs must have something to do with driving this molecular gas out. Okay, thank you.
Thank you very much, Kirsty. So we have one question in from Hannah Stacy, who's asking, how do you make the correction for opening angle and inclination, or how do you decide the inclination correction specifically?
Okay, so for the derived properties, we actually used a spherical geometry. So in that case, you don't have to think about the opening angle because it's just covering the entire galaxy. Which I guess is confusing when we then talk about a inclination correction, because then you're assuming that it's not a spherical geometry. So I guess these things don't really join up. Yeah. But yeah, I mean, using a spherical geometry and a covering fraction of like 100% is just the upper limit. Yeah.
Okay. Thank you very much, Kirsty, and thank you very much to all the speakers this morning. So we'll have a break now, if I understand correctly, of about 10 minutes, and then we'll continue with the second session of this morning or afternoon for some at 12:40, I would say. So thanks again to everyone, and we can continue the discussion on the talks through Slack. Thank you very much.
Thank you very much to everybody. Just a note, it's 12:40 in Chile, so 10:40 a.m. Eastern time. So it's just, we've been giving all times in Eastern time, so to not confuse everybody.